Please welcome Jano Costard, SPRIND, Federal Agency for Disruptive Innovation.
As head of our International Challenge Innovation Competition program, I see many extremely ambitious projects. And that makes you wonder, is that too good to be true? And you might also ask yourself that question when you see the next pitch. Because it does not only solve one of the crucial unresolved grand challenges of our time, but two at the same time. It's about defossilizing the chemical industry that provides the materials our world is built on, but so far is built on fossil resources. But it also solves that other crisis that we already have too much CO2 in our atmosphere, and we know that we need to get that CO2 out of there and do both actually at scale. We have been working with MacroCarbon for almost 2 years now, where there are currently finalists in one of our challenges. And over these 2 years, we learned that that team and its founder, Fernandez Mendez, is one of the most driven, ambitious, and powerful science entrepreneurs that are out there. And that's why we trust that that's not too good to be true, but actually is a potential breakthrough. So meet Fernandez Mendez.
Breaking the wall to defossilizing the chemical industry. Fernandez Mendez, MacroCarbon.
We all need plastics in our daily life. Think about your computer, your phone, your child's toys. However, in order to create these products, the chemical industry heavily relies on fossil fuels and at the same time emits CO2. The EU has put out strict guidelines to reach net zero to avoid this type of emissions. Now, using renewable energies, we can, of course, reduce the emissions from the manufacturing, the transportation, and the recycling of the plastics. But finding a renewable feedstock for the chemical industry at scale is non-trivial. There are a few sources out there of, for example, biological naphtha, but they're coming from trees and plants. And those at scale compete for space and for fresh water with food production. So our approach is to use the natural power of seaweed to absorb CO2 efficiently in the ocean and then transform that carbon-rich biomass into renewable feedstocks for the chemical industry. Now, in order to avoid the high costs of seeding kelp in coastal areas, we're using pelagic seaweeds, the ones that can grow floating, and they can grow in all areas of our blue planet, making floating seaweed a scalable solution to defossilize the chemical industry and also to sequester carbon. Our approach contains the whole integrated value chain from the aquafarming to the product. So our aquafarms are simple, they're flexible, they're either anchored to an existing platform or to the seafloor, and our floating seaweed grows fast in them without the need of seeding or complicating processes. The processing occurs on a nearby platform, and it has 2 steps: gasification with a high-temperature pyrolysis, and then transforming that gas into liquid through Fischer-Tropsch technology. This process, once it's running, it's self-sustaining. From that, we get 2 products: bionaphtha, which is a hydrocarbon, sustainable hydrocarbon, and biochar. And the biochar contains part of that carbon locked for the long term. Now, the bionaphtha can be immediately used in the chemical industry as a sustainable biofeedstock, and that market is expected to reach 1.1 billion by 2031. We can produce that bionaphtha at half of the price that is now being paid for bionaphtha in the market. So we have a good margin for revenue there. We can get carbon credits not only from avoiding emissions by substituting fossil fuels with our bionaphtha, but also from the biochar that does long-term carbon sequestration. So we have a pretty good, efficient way to transform the CO2 in the atmosphere into valuable products. And that's why this year we were winners of the Carbon to Value Challenge, as Jano mentioned, and we created MacroCarbon together with our founded partners, the Alfred Wegener Institute, where I used to work as a scientist, Seafuels and Carbon Wave, who are also startups in this field and are at the forefront of this. We are part of the European Biochar Industry Consortium, and we're also part of the Global Seaweed Coalition. One of our main supporters is BASF, who in their letter of support mentioned that growing seaweed precisely tackles this major source of CO2 emissions in the chemical industry. We also have partners in the UK for the processing technology and local partners in the Canaries, where we already have a team of 6 people working to develop this. This year and next year, we will do the research and development phase, testing the next prototypes, filing in the patents, also exploring different types of seaweeds. And then by 2025, we will have our first pilot plant next to the Plataforma Oceánica de Canarias. That's the size of a football field, roughly. By 2026, we will have the full-size integrated plant, which will be around 6 square kilometers, and this will bring us a revenue of 23 million euros in bio-naphtha and 2 million in carbon credits. For that, of course, we need to raise the funding of the Series A and Series B. After that, it's about upscaling in order to make it a reality that the carbon-neutral chemical industry will exist. Thank you for your attention.
You are also very fast. Wonderful pitch. So let's go timing for questions now. Who would like to start? You're not jury. Let me check the jury first. We have a jury first. Sorry. Please.
Thank you for your pitch, Ma. Can you tell us something about how much of the steps of the value chain you cover? So do you also do the post-processing? And how sure, if you do, how sure you are about the cost competitiveness?
So we stop at the bio-naphtha stage. So our clients would be, for example, BASF or Borealis, and they would then transform that bio-naphtha into the products. So the one product that we do sell ourselves is the carbon credits, but the bio-naphtha, we don't transform it into the plastic. So that can be used to produce either biodegradable plastics or non-biodegradable plastics.
Okay.
Sorry. The cost of the bio-naphtha?
The cost of competitiveness, I repeat because we don't have the microphone.
So currently fossil naphtha is sold at around $600 per ton. And bio-naphtha, so the companies that are willing to pay a premium for biological feedstocks, it's about $2,500. And we can produce the bio-naphtha at half that price. So we have quite a good margin there to make a win at scale, of course.
Thank you. So yes, I think Frank was slightly before you, and then you will be the next, and then I will come to the audience. Thank you.
Sorry about this being faster. Can you give us an idea to save 1 megaton of CO2 emission in the chemical industry? What is the size of the aqua farming you need to entertain? That means how many square kilometers of surface of the seaside you need to cover with your farming?
So I can give you 2 values. 1 hectare of our aqua farm stores around 100 tons of CO2 per hectare. And if you go up in the calculation, we made the calculation for 1 gigaton, just to be like very broad, you would need around the size of Portugal in the ocean to sequester that amount. But inside the Atlantic Ocean, that's actually not that big. We have a lot of ocean available in our planet, if we can go offshore. If we're restricted to the coast, of course, we're competing with other interests, but if we can start moving offshore, there's definitely enough space. But yeah, the challenge is there. It's gigaton scale.
Next question was, sorry, it was, yeah, you please here. Thank you.
Thank you. I would love to hear a bit more about the maintenance costs from these aqua farms, and I would love to hear what do you think about the ecosystem in general for the ocean in terms of aqua farming.
Yeah. So the maintenance costs are relatively low compared to other aqua farming approaches because you don't need lines in between, so it's just a barrier containing your floating seaweed. So it's less, but of course there is a cost there. And then in terms of the impacts on the environment, that's actually where I come from. And so what we've observed in the small trials that we've done till now is that actually you have a positive effect because this floating seaweed acts as a biodiversity hotspot, so fish like to come and hide below it. And of course, we will have to monitor as we scale up what the consumption of nutrients is, what the carbon sequestration is to the seafloor, like the natural carbon sequestration, and all that needs to be monitored. But that's exactly where my background is on. So I'm making sure that we have a set of arrays and include those measurements into biogeochemical models to be able to estimate what the impacts will be at larger scales.
Wonderful. I think, yes, we have a question over jury here. It will be the last question. Make it short, please, and short answer.
Yeah, quick and detailed. So if you go offshore with such a large area, if there's storm and wind, I mean, how stable is that? Is that destroyed every time there's a big storm?
So, of course, we don't know yet. Our prototypes haven't been destroyed by minor storms yet because they're very flexible, so they're not rigid. But we're also looking into options on how to sink the structure, like cover it and sink it so that it can pass through storms. However, the areas where we want to deploy this, in the subtropical gyres, for example, you don't have we're not going to do this in major pathways of hurricanes, for example.
Thank you very much. We're over the time already. And of course, your name is the program of this startup, right? This is wonderful.